Okay, now let us try to learn initial value theorem of Laplace transform. The statement of initial values theorem is if the Laplace transform of a continuous time signal x of t is denoted by x of s, then the then limit t tends to 0 x of t that will be equal to limit f tends to infinity s x of s, where x of s is the Laplace transform of given signal x of t. Okay, now let us prove the statement. Okay, right. Okay, before proceeding, we need to know the time differentiation property of a Laplace transform, which is not included in our syllabus anyway. We should know about the time differentiation property. So let us try to understand the statement of time differentiation property. Okay, this is the time differentiation property of Laplace transform. The Laplace transform of the first derivative of the given continuous time signal x of t, that means d by dt of x of t, that is equal to s into x of s minus, here this is small letter x, just take a look at x of 0. X of 0 means the value of x of t at t equal to 0. Okay, right, that is x of 0, not capital X of 0. Small letter x means the in the time domain itself. Okay, right. Now we know that the Laplace transform of a signal x of t, Laplace transform of x of t is equal to integral 0 to infinity e raised to minus st x of t dt. Okay, right. This is the basic equation for Laplace transform. Here I have taken only the single-ended Laplace transform, means actually in the bilateral transform the limit of integration varies from minus infinity to plus infinity. So now in order to prove this result, we have to take only the right hand sequence only. Okay, right. Therefore, what will be the Laplace transform of this one, d by dt of x of t? We know that this is the equation. Here, in place of x of t, now we have d by dt of x of t. So, in the RHS also, we have to make the modification. Okay, so let us replace x of t with the new signal. So here I am going to write d by dt of x of t. Okay, right, then followed by dt. Now let us mark this equation, means the time differentiation property. That's equation number 1, and this one is equation number 2. So I'm going to replace the left hand side using the right hand side of equation 1. I'm going to replace the left hand side of equation 2 using the right hand side of equation 1. Okay, what is Laplace transform of this one? That is s into x of s. I'm going to replace the LHS. Okay, minus x of 0. Okay, then equal to integral 0 to infinity e raised to minus st d by dt of x of t, then dt. Okay, now let us take the limit on both sides. Let us take f tends to infinity on both sides. In this case, so what we are getting is limit f tends to infinity of LHS. What is our LHS? Is x of s minus x of 0, then equal to again we have to take the limit f tends to infinity in the right hand side also. Okay, 0 to infinity e raised to minus st d by dt x of t dt. Okay, right. Now if the value of f become infinity, actually this equation will be e raised to minus infinity, right? We know that e raised to minus infinity is equal to 0. E raised to minus infinity equal to 0. So if the value of f tends to infinity, here also, here we have a term containing s. So this term becomes e raised to minus infinity. So the value of e raised to minus infinity equal to 0. So the entire RHS becomes 0. Okay. So let us rewrite this equation as s into x of s minus x of 0 equal to entire RHS becomes 0 as f tends to infinity e raised to minus infinity equal to 0. Okay, right. Now let us split this limit. Let us expand the brackets here. So what we are getting is limit f tends to infinity first time s into x of s minus limit f tends to infinity second time x of 0 equal to 0. Okay, now just take a look. Here we don't have any term containing s. Okay, so this limit f tends to infinity is invalid in this case. So let us rewrite this equation once again as limit s tends to infinity s x of s minus, this one is invalid, so let us simply write this equation as x of 0. Okay, and again the right hand side is equal to 0. If I took the second term into the RHS side, we are getting limit f tends to infinity s x of s in the left hand side equal to, this one become positive x of 0. Actually x of 0 is equal to limit t tends to 0 x of t, right? Then we are very much closer to the solution. So if we rearrange this equation, we are getting limit t tends to 0 x of t, that is equal to limit f tends to infinity s x of s. That is the required statement to be proved. Okay, right. Thank you.